while I was working on another video, the topic of special Euclidean group came up, which, roughly speaking, is a collection of all translation and rotation in space. And translations and rotations do not commute with each other. If we translate 2 steps to the right, then rotate 90 degrees about the origin, then we would get a different result if we do them in reverse, which is to rotate first, then translate 2 steps to the right. Now, the real interesting thing is, either way we compose these transformations, they end up being rotations about some other point in space. And that raises a couple of questions. Why did they end up being rotations about some other point, which is -1 and 1 and 1, 1 respectively? And the more important question is, can we come up with a formula for rotating about any point in space? And we will see in this video how that very technique that we're about to come up with has anything to do with solving partial differential equations, quintic equations, and Fermat's last theorem. If we translate 2 steps to the right, then rotate 90 degrees about the origin, we got the same transformation as rotating about the point -1 and 1. And if we do them in reverse, we get rotation about the point 1 and 1. And the obvious part is why it's 90 degrees rotation still. Either we rotate then translate, or translate then rotate, it definitely still is a 90 degrees rotation. So the part that we don't know about yet is why it's rotation about those specific points. And transformations themselves are hard to analyze, so it's easier to see what concrete objects they act on, which is a point in 2-dimensional space. So first, we will apply translation 2 steps to the right, then 90 degrees rotation. And since this combined transformation is rotation about some point, it should fix exactly one point, which is the center of rotation. And we just have to find that fixed point, which means a point that is unaffected by the transformation. At this point, this is just a system of 2 linear equations, and it has the solution -1 and 1. And similarly, if we solve for the fixed point of rotation then translation, then we should get 1, 1. We just knocked out the less interesting part, and now we want to find a way to describe rotation about any point. And in order to do that, we first have to get familiar with how coordinate transformations work. Suppose I am moving forward. Then, with respect to my frame of reference, which is my coordinate system that follows me, stationary objects like trees and street signs are moving backwards. And if I am rotating my body counterclockwise, then it is equivalent to everything else rotating clockwise to my frame of reference. And that's the intuition that we want to have for coordinate transformations. So let's say there's a point in space, and you may say this point can be described as an order pair 2, 1. And there is an implicit assumption that we made, which is the choice of the coordinate system. And every point in this coordinate system can be described as a linear combination of the basis vectors. Now, what if we translate the coordinate systems 2 steps right and 2 steps up? Then, the point that was originally 2, 1 in the old coordinate is now 0, -1. And if you know some linear algebra, you may say that C1 and C2 are not basis vectors, or not even vectors since it doesn't start at the origin. But they indeed are basis vectors, but of a different vector space, which we call the tangent space at the point 2, 2. And you can just think of it as a different vector space with a different origin. In any case, we can get a description of any point in the new coordinate system by subtracting 2 from each entry. Since the coordinates moved upright, it would be equivalent to everything else moving down left. So suppose we have this parabola, and we want to write down an equation to describe it. And it may not be too obvious how to do in the standard coordinate, but there is a coordinate system where it becomes really easy. And once we find the answer, we just have to translate it back to the language of the original coordinate. And in high school algebra, it's fairly common to solve it for y, which makes it somewhat extra confusing to understand the underlying coordinate transformation in action. It makes you think extra hard about why we subtract h but add k. You may not have realized it, but we just unlocked one of the most powerful tools in mathematics. Suppose we have a hard problem, which could range from mildly annoying to provably unsolvable unless we introduce a completely new framework. If we can find a way to turn the hard problem into an easier one, then we could solve it. And the translation into new language could mean anything from coordinate change, change in number system, or some obscure categorical equivalence. And once we find a solution, we can interpret what it means for the hard problem. This diagram could be a commutative diagram, which will be explained in detail later, or just a diagram that represents an algorithm, like a step-by-step guide to turn a hard problem into an easier one. This general process is like a mathematical backdoor, which can be applied for most mathematical problems. It's rarely the solve step that is the hard part, but the true challenge is finding an appropriate easy problem that would solve the hard problem. For example, consider the Fermat's last theorem for case n equals 3. And let's try turning it into an easier problem, say the same problem but over the real numbers. And it should be easily solvable by taking cube root on both sides. And it has infinitely many solutions for all real values of x and y. But this information is meaningless to us, since what we want to show is that there are no natural number solutions. And this shows that difficulty usually is in finding the appropriate easier problem. But there is a case where solving easy problem also guarantees the solution to the hard problem. And that is if there is a one-to-one correspondence between the easy and the hard. For example, coordinate transformation loses no information which way we go. In either coordinates, they describe the same object, just with different description. Now we're ready to tackle the main problem. We want to write down a formula that describes rotation about any point in space. And what we really mean by that is write down an explicit formula for a transformation in the standard coordinate. And I will call that coordinate x. Then the most appropriate new coordinate would be the one that has the origin shifted to the center of rotation. And I will call that y. Now, let t be the transformation that we want to describe but in the x's description. And x prime would be the resulting point after transformation. T is eventually what we want to get at, but it's too difficult, so let's try solving an easier problem. The same transformation but in the y's description. And that transformation is just rotation about the origin, which can be represented as a rotation matrix. Now, we just have to translate it back to the language of x. So we first substitute y for x minus the shift. And supposing y's transformation and x's transformation really describes the exact same transformation, but just in a different coordinate system, then y prime should be x prime shifted. This is a tricky argument to follow, so I think it's a good time to pause for a visual illustration. The yellow ball in the x's coordinate description would be 2, 0. And the y's coordinate description would be to subtract 1 from each entry. Now, we're going to apply some rotation about y's origin. Yellow ball's coordinate description in x and y is still 1, 1 apart. So the x prime and the y prime, which would be like the ball's position after transformation, are really the same point, just different coordinate description. Lastly, we just isolate x prime, and we finally have a formula for t. And if we really break down what t is doing, we first shift the coordinate system from x to y, make a rotation about the origin, then translate the language back to the x coordinate. And naturally, the coordinate change from y to x is the inverse function of the change from x to y. Now that we solved our problem, let's make a diagram out of what we just did. The upper arrow t represents the transformation that we are trying to describe in x coordinate description. And the easier problem is to describe it in y's coordinate, which is simply just rotation about the origin. And since each of these arrows represent some transformation, whether it's an actual transformation or just transformation of coordinates, we can compose them. So if we follow our diagram starting from x, then move down, then right, then back up, then we end up doing exactly the same thing as doing t. And if we really wanted to, we can describe what simple rotation would be for y's coordinate in terms of t by following the arrows up, then right, then down. This is an example of what mathematicians call a commutative diagram, which is a diagram where each arrows represent some function, and no matter how we compose the arrows, if the start and the end is the same, then they are the exact same function. And these types of commutative diagrams show up so frequently in every branch of mathematics that there literally are subjects that study these diagrams in the most general sense, namely the category theory, or more jokingly called abstract nonsense. In any case, we solved the problem that we set out to solve. So, can we see how similar technique can be applied to solve problems in other branches of mathematics? I will keep rest of the video pretty high level and treat it more like a history video and how attempts to find the backdoor, like we just did, led to some of the greatest discoveries in mathematics. And the first problem that we will look at is the Fermat's last theorem for case n equals 3. First step that we can take is to turn it into a slightly easier problem by extending the number system from the natural numbers to the integers. Integers have a lot of benefits compared to natural numbers since we're allowed to add, subtract, and multiply any two numbers. And in modern language, we say it is a ring. We want to prove that no solutions exist, so if there are no solution in an even bigger number system, then there are no solution in the smaller number system. But we have to be slightly careful with the integers since it contains 0. So we have to exclude what's called the trivial solutions, which is when any of the number is equal to 0. In 1760, Leonhard Euler came up with a truly marvelous proof, which is to extend the number system even further. To explain what this means, we will start by looking at an easier example. This is a number system where you have all the integers, but you also add the imaginary unit I to it. Now, can we just call it a day here? Well, no, for a number system to be useful, it needs to be a ring. So we should be able to do 1 plus I, or 2 minus I, and be able to add and subtract and multiply any two numbers. We call this new number system Z adjoin I, or more commonly the Gaussian integer. And over this new number system, expressions that were not factorable now becomes factorable. Now, as per the Euler's new number system, it is Z adjoin omega, where omega is this weird number. But if you are familiar with some trigonometry, you may recognize that this number is a unit complex number at angle 120 degrees. And if you are familiar with some complex arithmetic, it is also called the principal cube root of unity. And in this number system, you're allowed to factor sum of cubes into its linear factors. And if we graph all the points of this number system, it would look like an integer lattice of equilateral triangle. Now, back to the original problem, maybe you can guess why this new number system is easier to work with. But I won't go through the proof in this video, since it just wouldn't fit into the margin of this video. But this marks the start of a new field of mathematics that we now call algebraic number theory, which is the study of number theory over these new number systems that we now call number rings, which are extended versions of integers. So couldn't we just try to use the same technique to solve Fermat's last theorem for every different power? Well, not all number rings are made the same. For example, Euler attempted to solve the case n equals 3 several times, coming up with faulty proofs. In one of those faulty proofs, he was working over this number system. And in this number system, factorization of numbers into primes is not even unique, which led to a faulty reasoning. In the language of modern ring theory, we say this ring is not a unique factorization domain. In any case, Euler's attempt to turn a hard problem into an easier one, he discovered that some number systems are easier to work with than others. And the subject of algebraic number theory blew up with attempts to classify these different number rings and their properties, and they are a crucial part of computer cryptography algorithms today. Now, let's look at a different problem. This is a quadratic equation, and in order to solve it, we typically use the quadratic formula. And if you have never seen where the formula comes from, We first divide by a on both sides, subtract the constant term, add a special number on both sides so that the left side is a perfect square, and I just showed you the most crucial steps, so rest is left as an exercise. In any case, quadratic formula is derived from a key technique called completing the square. Now, the natural question that comes next is, can we come up with a formula to solve a cubic equation using some clever technique? And answer to that is yes as well. And if you are keen, you can spot the number omega in the formula. Then, how about for quartic equations? The formula does exist, but it's really long and no one really memorizes them in practice, unless you are the type of people that would memorize 1,000 digits of pi. Then, how about for quintic equation? Well, a general quintic formula does exist, but can we come up with a formula expressed by algebraic operations and radicals only? And nothing transcendental like sign or exponents, and anything else that would involve infinitely many operations, since that is not algebra anymore, it's calculus. And answer to that is no. There is no general quintic formula that only involves algebraic operations and radicals. The first proof was given by Paolo Ruffini in 1799, and he had the right idea, but there was a hole in his argument. Then in 1824, Niels Henrik Abel builds upon Ruffini's idea and comes up with a complete proof. And then soon after, Évariste Galois builds upon the theory and generalizes the result for any polynomial. This problem was an unsolved problem for centuries, and many mathematicians try to solve the equation directly, since that would be the most normal thing to do when you have an equation. But that, we now know, is an impossible problem to solve thanks to these three mathematicians. And their backdoor approach to the problem was so novel that most mathematicians at the time thought it was abstract nonsense, and their works were only recognized posthumously. And the new mathematical tool that they invented is called groups. So what is a group? It's a collection of actions that preserve a certain symmetry. In the very beginning, we looked at special Euclidean group, which is a collection of translation and rotation. And the symmetry it preserves is distances, shapes, as well as orientation. And if we choose to preserve distances and shapes only, but not orientation, then reflection is allowed as well, and this group is called Euclidean group. In the context of grade school geometry, the Euclidean group, which is made up of translation, rotation, and reflection, preserves congruence of two shapes. When Galois coined the word group, he really only meant finite groups. Like the group of rotations of a square, which we call the cyclic group of order 4. And the group of all symmetry of a square, including the ones that do not preserve orientation, which we call the dihedral group of order 8. And the group that we're most interested in is the group that represents the hidden symmetry in a quintic equation, which is called the symmetric group on 5 elements, which is the group that represents unrestricted permutation on 5 objects. And these objects represent 5 roots of the polynomial. And these groups that we have seen can factor into smaller groups. First, the Euclidean group can factor into group of reflection and the group of translation and rotation. And the group of reflection here is the cyclic group of order 2, since the reflection is a 2-cycle. And the special Euclidean group can further factor into rotation and 2-dimensional translations, which can further split into 2 copies of 1-dimensional translation. Is this a complete factorization? Well, no, infinite groups are kinda weird, and these groups can factor infinitely more. But at least for finite groups, it is possible to get a complete factorization into simplest building blocks, which is kinda like prime numbers. And we call those simplest pieces simple groups. So now, for the group of symmetry on a square, it can split into reflection and rotation. And since the rotational symmetry on a square is made up of multiples of 90 degrees rotation, we can factor out just the multiples of 180 degrees rotation, which would just be 2-cycle. And whatever the other factor is. And I cannot provide a geometric intuition behind what that last factor is. But if you happen to know some homological algebra, it's because the quotient is not split. In any case, this is the complete factorization of D8 into simple groups. And notice how all the simple building blocks are cyclic groups. Galois proved that a polynomial is solvable by radicals when the group of symmetry of polynomials factors into these cyclic groups. However, the group for general quintic equation factors into simple groups that are not all made up of cyclic groups. So a quintic equation in general cannot be solved by radicals. If that completely went over your head, that's totally fine since it also did for most prominent mathematicians at the time. And we just speedran like 3 semesters worth of abstract algebra in a 5-minute segment. Anyway, the trio turned what was an impossible problem, which is to find the quintic formula, and turned it into a problem about behaviors of different groups. And in the process, group theory was born. And to this day, it is one of the most valuable tools in mathematics. Previously, everything was thought of as equations to solve. But after group theory reached the mainstream, people started describing things as transformations or actions or operator, and people started looking for symmetries in things. And the main way we classify topological spaces, which is to count all the different ways a space can have a hole, is done in the language of groups. And the standard model, which is kinda like the theory of everything except for gravity, has symmetries that are in the language of groups. And if they look familiar to some of the groups that we have seen before, they really are. For example, SU3 is kinda like the group of rotation of 3 complex dimensions, so it's kinda like rotation in 6 real dimension. If you want to learn more about groups, my next video is going to be about deep connection between groups and rings as a part of my series in ring theory. And I want to highlight all the hidden symmetry in number systems, so please subscribe if you want to see groups in action. Now, shall we talk about some partial differential equations? This is called heat equation, and it models the flow of heat. It was first derived, then solved in the same paper by Jean-Baptiste Joseph Fourier in the year 1809. And he solved it using a technique that we now call Fourier series, which says that any reasonable function in an interval can be represented by infinite series of sines or cosines, or maybe both, depending on which one does the better job for the situation. And for this very specific example, cosine series seem to do a better job, since the sine series has to be 0 at the boundary. Also, notice how fast cosine series converges compared to sine series. In practice, we choose the one that satisfies the boundary condition, which we will see in a bit. Instead of heat equation, we can use practically the same analysis on wave equation. So let's do that. The biggest difference is that there is an acceleration term on the left side instead of the velocity term. And one intuitive way we can think about it is that the more concave the function is in the spatial coordinate, the bigger the acceleration will be. Now, c here stands for speed of the wave, so we can scale our coordinate to make it equal to 1. So instead of measuring lengths with meters, we can use units like light second or Mach second. Now, in order for the equation to have some realistic meaning, we have to specify some boundary condition. So if the wave represents string of a guitar, then left and right endpoints must equal to 0. And we have to specify a couple of initial conditions as well. And the first one is the initial position. And you can think of pulling on a string and letting it go. And the second one is the initial velocity, and you can think of it as strumming on a string. And it's totally possible to have both, but for simplicity's sake, let's set the initial velocity equal to 0. And now we have the complete problem. Fourier first recognized what types of series would be the most useful, and in this case, it would be the sine series since they are fixed at the boundary. Then, he was able to write the initial function as a sum of these sine functions. Next, he noticed that if the initial function happens to be one of these simple sine curve, then the solution was just the product of sine of x and cosine of t. So if the initial condition can be written as a sum of signs, then the general solution can be written as sum of individual solutions. When Fourier came up with this technique, he didn't quite understand the implication of this. He thought it was just some clever technique. But there was a reason that I chose to demonstrate wave equation instead of heat equation. Fourier's discovery was the very language that describes actual waves in nature. If we look at the formula, the spatial frequency and the temporal frequency is the same. And if we didn't get rid of the wave speed constant, they're at least proportional. So if we look at these individual modes of vibration, the higher order terms actually vibrate faster. And every wave has to be in a superposition of only these states. And this is the spectrogram for those three plugs. The horizontal axis represents time, and the vertical axis represents frequency. And as you can see, the frequency spectrum is not continuous, and it can only exist in these discrete or quantized states. If we look at the wiki page for superposition principle, it says Bernoulli had the right idea about the nature of waves. But Euler and Lagrange, who were the greatest mathematicians at the time, thought it was just a mathematical trick rather than a physical principle. And only after the works of Fourier, the superposition principle was accepted as mainstream. And how did we get this graph in the first place? Well, we use a tool called Fourier transform to pick out what frequencies were in the wave from a continuum of all possible frequencies. And Fourier invented it to solve, as you guessed it, more heat equation. So Fourier, in order to solve a really difficult equation, invented one of the most useful tools of mathematics that we now call Fourier analysis. And it's applicable to pretty much anything regarding waves, signals, and repeating patterns. And the very video that we are watching uses a form of Fourier transform for its compression algorithm. And if you're curious to learn more about how Fourier series can be generalized, I have a couple of upcoming videos planned on theory of Hilbert spaces. If you're solving a hard problem, whether it's evaluating a difficult integral or a research in forefront of modern mathematics, you are looking for ways to make it easy. And the very reason we study advanced mathematics in the first place is so that we have more tools available to make difficult problems understandable, and we can find the deeper meaning hidden behind the problem. And maybe one day, you can come up with your own groundbreaking discovery. So remember this diagram when you're faced with a difficult problem. Thank you for watching.